this is the password, this is the login, and you have to take the node name like Tute14 over here, and I'll just open up a browser window and I'll say https tute14014.supercontainers.org, 8443 is the port number, and /e4s. And with this, it will allow me to log in, and we'll just follow the instructions here. I'll say that login name is tutorial, the password is HPC Linux 12 exclamation. I'll log in over here. It may bring up another window where I have to press the space bar so I can re-enter the password again. Okay, just a little HPC Linux 12 exclamation. Now there are a bunch of other files over here, and I can open up a terminal window here on this, and then use the SSH-y. Now I must warn you that the PDF file that you have, where you have these commands, you may be tempted to just cut and paste from that PDF on the command line, okay? But remember, our friends in the Microsoft PowerPoint, they mess up those dashes so beautifully that it will not work. So look at the PowerPoint PDF and then just type in those commands explicitly yourself, okay? So I will try that with SSH-y and then theta.alcf.anl.gov, like that, and then do the rest. You all have logins. Okay, so here I have the hands-on, and I have some examples over here. So first let me just go through an example on Theta. I have launched this with SSH-y, and what I'm going to do is I will try and get a node using our queue at ATPESC 2022 with the account at ATPESC 2022, and just expand this workshop in your Scratch directory, okay? And we'll look at an example like src MPI from CoMD application. So what I'll do is, let me just go to my src and make ATPESC. Now here I did a tar xf, and it is soft perf tools tau workshop.tgz. Okay. Now I have this workshop directory. I will try and get a CD to the workshop directory, and I will CD to the CoMD src MPI. And let me say make clean and make. This is an MPI application, molecular dynamics application. Just a show of hands. Is there anyone in here who understands molecular dynamics? Or wow, okay. So that's great. I may need your help in interpreting the data that we get. Okay. So this is an MPI application. We are going to run it on Theta. But before I run it, let me just say X term over here. Just make sure X is working okay. Now this is going from Chicago to Oregon, where AWS is located. And the X, okay, it's working. It's working here. Okay, so let me just do a q sub -i -a ATPESC 2022 -q with ATPESC 2022, and then I need to give it the number -n1 and then time, maybe 50 minutes. Okay, so here I'll get the interactive partition. Now if I had just copied and copy pasted it from the PDF, this would not have worked. those who tried to do that. Okay, this Q sub command, it will allow me to get a node, a single node that I have requested, and I will then go and run this co-MD example right here. You see in the bin directory. Let me go and check that it created this in the .bin directory ls. It created this co-MD MPI. Now just have a look at the r.sh file. All it's doing is it's using app run and then running it on 16 cores with 441 and running nx, ny, nz as 80, 80, 80. Okay. Here is the theta mom node here. So I'll go to src ATPESC co-MD workshop co-MD bin. And then here is the r.sh. I can just say r.sh like this, maybe. And it will run the app run command, loading the Intel module, and it's running this code. Okay. It will take about 2 minutes to run this code. We are interested in understanding where those 16 MPI ranks are spending their time. Okay. We are interested in instrumenting the code at the MPI level and then turning on sampling at the rest of the code. So as it's running here, let me just show you how we are going to use it with tau. We are just going to say cat r.sh. This is the application run. And then rt.sh. So all I did was I added a module load tau and I added tau exec-ebs to the launch command. That's all. All I did was use app run with tau exec-ebs. And then it will generate performance data from each MPI rank. I'll be able to view it using paraprof. And my goal is to find out where is it spending the time at the routine level, at the MPI level, and right down to the statement level. Can I see where it's spending its time? Now I can pack the profiles and bring them to the AWS node and launch paraprof directly because AWS node has tau already installed on it. Or I can just do a remote X display. It will be faster than doing it from my laptop. So here it ran about 106 seconds total time, 106.55 seconds total time, and I can say rt.sh like this, and as you know, it just has the tau exec-ebs. So it's now running with tau. It may take maybe a second more than it did before, but I want to find out, did it do MPI collective operations? Did it spend a lot of time in the collective sync? Which functions were called? Were all the functions equally important, or did one function dominate the execution? What was the name of the function? Where was it located? I know nothing about this code because I just compiled it with optimization turned on with the debugging symbol. And all the collation of that samples that we collect and translation into the source location happens right at the end of execution in parallel. And so we generate the profile files and then we'll just be able to launch paraprof directly over there. But I think there is an issue with running X applications from the compute nodes. So I have two windows, one on the login node, one on the compute node. I won't launch paraprof from the compute nodes, I'll just launch it from the login node. Or I could just say paraprof -- pack and get a ppk file like foo.ppk, SCP it over to my laptop, launch paraprof locally, or launch it on the AWS partition. Now it's out of 100, it has gone to 80. It's about to be finished. Let me just do an ls over here. And there are no profile files yet. It's still at 90 out of 100. So it's computing, it's keeping all the profile data in memory, and then it will just write it out at the end of the execution. And now if I do an ls, I should see profile files written from mpi rank.0.threadid. This is a single threaded program to start with. So I will just say module load tau. This brings me a paraprof. And I can say paraprof ampersand. Okay, is this okay? I did a module load tau in the directory where the profile files are located, and then I just launched paraprof. Now, my goal is to understand what happened in the code. Which functions were called in each MPI rank? Do they all look similar? Do they look different? Here is the manager, it's loading the data, and there it is. All of these functions in their own space. So I can go here and right click here and pick the thread statistics table. I am over here where it says MPI ranks. And I can pick show thread statistics table. Everyone with me so far? So I'm just randomly picking one node and saying show me for say node 1, what is the thread statistics table? So here it's telling me, you saw that it took 106.55 seconds before. Now tau is reporting it took 106.9 seconds with the instrumentation. Okay? Out of that 106.9 seconds, it says MPI send receive took about 1 second. You see that 107 over here. MPI collective sync was not bad. It was just 0.015 seconds the time wasted in a barrier. So the code is responsible for doing all the work in this case. Unusual, but true. And here it's saying, look at the .tau application. 1 second was spent in the rest of the code in MPI. 105.6 seconds were spent in the .tau application top level timer in the collective in the application. So here is the profiler, and it's saying that I could not explain everything with sampling. In this case, I can explain 102.1 seconds, okay, out of the 105 seconds. But I can show you what happened in the rest of the code for 102 seconds. So let's look at this .tau application and expand it. I can also expand this. Let me just go full screen here and also move the columns around so I can see line numbers and all. If I hit this button over here, I can sort by exclusive time, ascending order or descending order like this. And look at that. It is saying that out of the 102 seconds, 95 seconds came from just one function. 95 out of 102 came from LJ force. Okay. There are other functions too. They sort atoms in cell, load atom buffer, advance velocity, get box. None of them account for much. It's saying if you want to drill down into this code, that red hot box at the top, that LJ force, that's where all the action is. 95.3 seconds are spent in this LJ force. Well, I can open this box and I can see the samples. So here it's saying at line number 189, I got 354 samples. It is spending 17.6 seconds in this line of code. Here is line number 198, where it's spending 15.8 seconds. Okay, line by line profile showing you 10 seconds here, 11 seconds here, 15 seconds over here. I can right click over here and say show me the source code. Okay, show the source code like this. And then I click show the source code, and it opens up this window right here. And it says, here is the function LJ force, and this is line number 198. There is a for loop. Do you see this? There is a for loop, there is a second for loop, there is a third for loop, there is a fourth for loop, and there is a fifth for loop. 5 levels of for loops, and right here at this line of code, it is spending 15.849 seconds in this function. Now I need some help from those who understand molecular dynamics. What is this function, LJ force? What is it doing with these particles? And is this typical of molecular dynamics codes like that, where they are iterating over all these for loops? I'm a computer scientist by training, so I know very little about molecular dynamics. But this is just a code where this Leonard-Johnson function, which calculates some sort of force, is taking up 95 seconds in just this one function, and you can see what it's doing right here. And you can see a statement by statement profile which shows the exact line numbers, and you can even pull up a window which says, show me how this function did across all the nodes by saying show function bar chart, like that. And here is the function bar chart. It's taking anywhere from 15.8 seconds on node 1 all the way down to 13.29 seconds on node 7. This line 198 right here. Okay, and recall that all I had to do was just change this by adding this tau exec-ebs in my code. That's all I had to do to generate this data. And of course, module load tau. But that's all I had to do to generate that. I launch paraprof, and then I can see the statement by statement profile. How did I do that? Once I got the paraprof window, let me just repeat this. Once I got the window, I went here, and then I right-clicked here on max, double-clicking two fingers, and show thread statistics table. There is a number of things that we can see, but I'll just start simple. Show thread statistics table in paraprof. I opened up the key for tau application, and out of this, I can sort it by clicking here, by clicking there. I opened up this LJ force, and then I moved this a little further, see the line numbers, and then go down to a particular function or a line, and then just say show source code, like that. Any questions? Are you able to do this? Can you first of all log in to the AWS instance? Are you able to SSH to theta, get a node, run the MPI job, launch paraprof, and get to a source line number like this? We'll just take a few minutes to have everyone catch up, but if you have questions in the meantime, please ask. And if you have a background in molecular dynamics, please look at the source code and see if you can figure out what is going on in that CoMD application. And is this where you expect it to spend its time? That's the more important question. Yes?
So I just missed what you said actually. If I just do like at the end, paraprof ampersand.
Yes.
Is the paraprof window just launch on the AWS?
Yes. If you have done the SSH-Y, then yes, from the login node, not the compute node, but on the login node, it will come up. But you must do a module load tau and then say paraprof.
So I need to get out of the compute node and Then
So that's why I started out an xterm so that I could do the compute node in the xterm. And then so I had two nodes, two windows. So, but the GUI should be launched from the login node. Okay? Or you can pack it, bring the file over, launch it locally. That you can do on your own. And even if you don't have the AWS instance, you can just do SSH-y and do the remote X forwarding, or you can just pack it, bring it to your laptop, install tau locally, and get this. I just wanted to real quick look at one more example, maybe with kubectl, with CUDA, with using a GPU. Okay, and let's look at the instructions here. This is theta. Then there is workshop tarball. This is OpenMP tools interface. You can see that I have theta GPU here with just plain single threaded example. Here is an example of CUDA with a matrix multiply. Here is one with MPI and GPUs. So let me try that. And here I'll just press the space bar and enter the password and come out of this. Okay, let me exit from this as well. So here is the login node. I say module load cobalt GPU, and then I will say q sub dash I dash a ATPESC 2022 dash q single dash GPU dash n1 dash t, say 25 minutes. I'm just getting a single node on the theta GPU, which has the A100 GPU. Okay. Once it starts, I'll go to the cloverleaf example, which is a CUDA example that uses MPI. I'll compile that. I will launch it without tau. I'll launch it with tau, and then see the performance data. Okay. Here I've got the theta GPU. Okay. And now I'll say cd to my scr ATPESC directory. I'll go to workshop, cd to the cloverleaf example, and then cloverleaf CUDA. I do a make clean, I do a make. This is interesting because it uses MPI along with NVIDIA NVCC. Okay, you see this NVCC over here? It's compiling these kernels. It will create an executable which uses MPI with CUDA, and it will do some computation in this cloverleaf benchmark. I want to find out how much time is spent in those GPU kernels and how much time is spent in MPI. So I can say MPI run dash NP3, and then the name of the binary over here. .clover underscore leaf. Okay. Do you see it says MPI, it found A100 GPU and is running. This is all there in the slides in the hands-on session about cloverleaf, and there. With the number of iterations I specified, it says it did not pass the test, but I don't care. I'm just running it for a small number of iterations. I'll just run this again, but I need to do a module use tilde samir module files. and then module load tau. So which tau exec, it's in my path, and then again I will run this tau exec dash t kubT with MPI and enable kubT and maybe even event-based sampling, and then run this code. Again it sees A100 and is running the whole code, and with this I will be able to generate the data on the GPU, and there it is. So theta GPU, let me come out of this interactive node, because on compute nodes I cannot run X, I can only do it on a login node. I'm back on the theta login node. Module load tau. If you are getting X Windows errors by remote X, it's most likely that one, you have not used SSH-Y when you logged in, or you tried to launch this on the compute node instead of the login node. Okay, always do it on the login node. I did a module load tau, and then I will go to this cloverleaf directory with cloverleaf CUDA, and here I will see that there are profile files that I will see in paraprof. So now I can launch with kubT or the CUDA profiling tools interface, kubT. Okay, and I'm launching paraprof over here, and there is, you see over here that I had 3 MPI ranks. So with each of those 3 MPI ranks, you see MPI rank 0, 1, and 2, and there is a A100 GPU thread here and the host thread here. So there is a host profile which is different from the GPU profile, and if I open up the thread statistics table on the GPU, show thread statistics table, here is the table. I can see the memory copy from device to host, host to device. I see every single kernel that was running on the GPU there, and the time spent in all of them is negligible compared to the time wasted in the .tau application. Let's see what the host is doing. Right click here, thread statistics table. MPI collective sync is about 0.4 seconds, not bad, 14 seconds total, and it is doing a lot of MPI wait all. CUDA device synchronize is taking 6.8 seconds. CUDA mem copy is taking 2.7 seconds. You can even go inside this, see wait all, and see exactly what it's doing in the wait all. Now mind you, I do not have the source code of this MPI, okay, but I can see that there was a user called ASCOVEL, and in this user's directory here is the full function that took 0.4 seconds. UCT CUDA IPC interface progress, it's just waiting on some progress nodes. Somebody compiled this at this line number over here. So you can just see, by this I mean I can go inside libraries that are outside of my application. I can look into MPI calls, I can look inside all the source code and see where the time was spent. Do you think it will be possible to see this level of detail inside CUDA mem copy to figure out what it's doing, or device synchronize? It is spending a lot of time in this driver libcuda.so, 4.8 seconds. VDSO, it was doing a pthread mutex try lock, libcubT. So I can't get much because it's a vendor library, they've closed it, but I can still see what it was trying to do in this device synchronize. It's just waiting for memory copy. You can see how much time was taking place over here, and 2.1 seconds in this libcuda.so. So it gives you some information, a lot more information over here of all the things that were going on in the application. And here in the application code, I can see the mutex unlock full and unresolved. So it's doing all these CUDA launch kernel calls and CUDA calls on the host side, and then you can see exactly how much time was wasted in the MPI operations. So this is the MPI collective sync, and I can see in the function bar chart that it took anywhere from 0.02 seconds wasted time to 0.69 seconds. You can also compare two things, like you can right click here, say add this thread to comparison window, and then you can see what this node was doing. Then you can move it over and say add this thread to the comparison window. And then you can compare what happened in relative timings. Look at that. CUDA memcopy took 9.6 seconds on node 1. And then MPI wait all took 2.9 seconds here. Device synchronize was less here. So CUDA memcopy on this node took a whopping 9.6 seconds out of the 14 seconds. And you can see where it came from and the exact calls. Any questions so far? Does it look okay? Does it look like you can use this tool to see the performance of OpenMP calls, MPI calls, your application profile, CUDA calls? It's not any different for level 0 or ROCm. You just have to have tau installed, and if you would like, you can just use the containers from E4S or SPAC to install tau yourself. Yes, go ahead.
During install SPAC, you have to like specify like with CUDA or OpenMP or MPI.
So there are variants, that's right. So you can say SPAC info tau, and it will show you what options you have. And then you could say SPAC install tau plus MPI plus CUDA or plus ROCm or plus level 0, and then pick the GPU runtime to install it. SPAC is just a package manager. It has recipes. By default, it may install an MPI version, okay, just a plain MPI with tau. But if you want any specific GPU runtime, then you must specify that in SPAC. Or you can use tau's configure too. You don't need to have root to install tau anywhere. You just have to have user permissions. And it just typically takes less than 5 minutes to install it. Yes?
I have one unrelated question. How easy it is to create a tree of all the functions code visited?
You just have to say tau call path equals 1, and then he asked, how do I create a tree of all the functions? So you have to turn on the call path profiling, and then you can specify call path depth and then start run that. There's an example of that in the SRC OpenMP directory for CoMD, and you can try that example. Okay, and even later you can try this on your own. Try these examples and send us an email if you have any questions. Does that sound okay? Yes?
How do you get the percentage of time in each function?
The percentage of time in each function?
Yeah, well, what you were showing, because I have the traces, but I don't get that analysis.
So here, this is the percentage of that. So this is not it is relative. It's like a comparison between two nodes. And to do this, what I do is I just right click on any here. I opened up this window by just clicking on this, saying, say, right click here, show function bar chart. Then after that, I looked at the two extreme nodes and I said, can I compare the performance of this one, which is taking the most time, by adding it to the thread comparison window, like this, and then go to the other node, here, node 0, thread, node 1, thread 0, and then also add this to the comparison window, and then blow it up and see that this is 2.1 seconds in CUDA memcopy, this is 9.6 seconds. 9.6 seconds is 438% of 2.1 seconds, like that. So do you feel comfortable now in using tau? If you had another project that used, say, Fortran with C or C++ with MPI, and you had a batch submission script, do you feel comfortable in saying module load tau, tau exec-ebs before the name of the binary, generating profile files, launching paraprof, drilling down to the function, and seeing where the time is spent in MPI, seeing where the samples are collected? Okay. That's really all there is to it. You just create a profile file and turn on sampling, or you can turn on just execution. In many of your application frameworks, whether it's using Cocos or libraries like PETC or other libraries, you may already have instrumentation that can generate like MPI functions or CUDA functions, such calls.
How did you open that window?
This window? To open up this window, I used the show thread statistics table by right-clicking over here, and I see a whole chart, and then I say show thread statistics table. If I forget that, I can always go to Windows right here and then pick a function or a thread window. So here I can say thread statistics table, like that, for a thread, and it says which thread. Okay. I can say I want thread 1, node 1, context 0, thread 0, and then I click select, and then it brings up the same window. So I can open it up in multiple ways, like that. Okay, with this we are at 6:28. I would like to thank you for your attention, but we have one more question before.
So it should be straightforward to install tau as a module on like the university cluster.
Absolutely. I recommend using SPAC or E4S as a full container which has tau already in it. You can pick from one with GPU support of 3 different GPUs vendors, or you can use just SPAC install tau, or just configure with the flags that I showed you. I showed an example command line for configuring it, and then you can install it. And again, thank you for your attention. I appreciate your participation in this ATPESC workshop. And let's stay in touch. Please send me email if you have any questions, or write in the Slack channel, and we can discuss any questions you may have, or even hold a screen share session if you have further questions. Okay? Thank you.